Hello again, everyone. I think we can start the webinar now. So thank you for joining us today. My name is Corentin Jouvet, and I'm Sales Manager at PowerSys. So I will start with a very short introduction before to let my colleague continue with the presentation and demo. So PowerSys is the leading provider of software solutions and services for electrification and grid, among other in electromagnetics. So we will discuss today about this part with JMAG software. Today we are presenting IPM motor topology optimization based on NGnet method. To develop this topic, I'm very happy to welcome Didier Tefac, our JMAG technical support engineer at PowerSys. Didier will present us the capabilities of JMAG for running such topology optimization with presentation and a live demo. And at the end, we will keep a few minutes to answer your questions. So if you have any question during the presentation, please type them into the chat box in your GoToWebinar control panel, and we will try to answer to the maximum of them by the end of the presentation. So Didier, can you hear me?
I can hear you.
Okay, I can hear you as well. So I let you share your screen and start your presentation.
Okay, good. So thank you for everybody to join this webinar about the topology optimization. So today I will start by a little presentation. So the agenda is divided into three parts. So I will start by general presentation of the topology optimization, focusing into the NGnet method, and then I will start with the demonstration using some IPM motor, and then I will finish by giving some advantage, limitation, and the feature development of this method. Okay, so here you need to note that the topology optimization so is the mathematical approach that optimize the material design of a specific design space, and JMAG will be able to find the optimal distribution of the design space, which can give you, for example, the maximum of the torque or the minimum of specific function. So it is a good design concept to explore the whole new topology without using the CAD parameter like the classical topology optimization. So here I will not detail all the optimization type and method that we have into JMAG, but what I want to explain is that into the topology topic, we have two methods, and today we will focus on the normalized Gaussian network method. So into this method, you will see that we will start by selecting the 2D or 3D domain. So for example, the surface or volume, and then based on the boundary domain or the material, we will try to find the optimal material distribution of the design region. So here during the demonstration, we will try to use also some optimization solver. So into this method, we have two types of solver depending on the objective function that you will set. So the step to create the topology optimization is very simple. So we start by defining the design region and apply the material of each part from the design region. Then in the next step, we will apply the topology condition where we will specify the selected design region. we will define the covariant matrix. We will also define the center coordinate of each Gaussian function here, and we can also take into account the symmetry in order to uniformly distribute the Gaussian into all the design region. Yeah. So into the next step, I will also show how to define the objective function, how to select to specify the solver, and how to run the calculation and get the optimal model that you can compare with the reference model. So before starting the demonstration, I need to give some recommendation of some cases. So for the first step, so what you need to understand is that the design region you need to be divided by the number of material that you will use for the observation. So in this example, for example, I have four cases. So in the case one, I want to use the wall rotor shape as the design region and use two material design. So iron and the magnet, for example. So this means that here I will divide this design region by two. So this is just one example, but you can also divide like this. So you have many possibility, but this is just one example. So here I want to design the whole rotor shape, taking into account the shape of the hole and using two types of materials, so iron and air, for example. So this means that this is how I will represent my design region. So here I will model one part and apply the air, which will represent my hole. In the next example here, I don't want to use the whole rotor, but just a specific region of the rotor. So here, this means that I need to divide this specific region by the number of design material. So this is one example. And to finish, here you see that I use three design material, and I want to use all rotor and taking into account the whole shape. So this is how I can divide my design region. So when defining the topology condition for the NGnet method, so you need to note that all the Gaussian cell will have the same standard deviation or the same covariant matrix. Yeah. And you also have several methods to define the center coordinate of each Gaussian cell. So you can import some CSV file, or you can use this tool to automatically generate all the grid of the Gaussian. So by specifying the space dimension along the X and Y axis, yeah. You can also take into account the symmetry, because this is my design region. You can see that this two part is symmetric over along this line. So here you can see that we can also use this option to make sure that the distribution of the Gaussian is uniformly distributed, is the same into the two part. Okay, so note that into JMAG, the NGnet method was implemented by using two model, for example. Two model, you have the sample model, the binary material model, where you can only use two design material. So this means that the material of the rotor, for example, we have just two states. So for example, the state on correspond to the iron, and the state off will correspond to the air, for example. And you can also, the other model is the multi-material model, where you can use more than two material. And this means that you can set various design materials such as iron, magnet, air, and so on. So previously, we have seen that how the center coordinate of the Gaussian function can be generated into the design region, and also how the covariant matrix of the single function is defined. So now, what is important is to understand how the shape of our design region is expressed in terms of linear combination of the Gaussian function. So if we take one section here, of the design region, you will see that the Gaussian is uniformly distributed into this area. And after normalization, each cell will have some normalized Gaussian function, and each cell will have some JMAG will apply some specific coefficient. So some weighted coefficient to each cell of the design region. And finally, the shape function. So the shape function will be the combination of the weighted coefficient of each cell times the normalized Gaussian of each cell. So this function will represent my design region, and this is the function that JMAG will use to optimize the shape, the shape of the rotor. So here, for example, here we have two type of two design material. So this means that the result, the value of this function will give the type of material. So for example, if the value is positive, this means that we have the metal or iron. If the value is negative, we have the air. So what I want to say here is that the final objective is to find the optimal weighting coefficient. So is to find this coefficient that optimize the shape function, in order to obtain the maximum or minimum of definite function. So into the solver configuration, you will see that you will have two types. When you are using this NGnet method, we have two types of solver depending on the type of objective function. Yeah, and you also have some recommendation about the specification of the setting. Yeah. So let's start with the one example. So this is the step that I will follow just to show how we can create this kind of topology optimization using the NGnet method. Here, this is the model. So I will use the quarter model of this full model. So the objective is to find the optimal rotor shape here that maximize the torque average and minimize the torque ripple. So I will use a magnetic analysis. So the design domain is the 2D rotors. So is these two rotor part. I will not use the magnet, and I will use this design material. Okay, for the NGnet setting, so I will use this setting to define my covariance matrix, and also this setting to generate the grid. And then I will also show how to use the mirror option in order to uniformly distribute the Gaussian, and we will confirm the number of Gaussian that we will use to define the setting of the solver. Yeah. So here you can see that here I will show you how to define two functions. For example, the function that will optimize the torque average, the function that will represent the torque ripple, and depending on the object function that you will create, you will select the corresponding solver. Okay, so let's start with the demonstration. So here I will open the demonstration model. Okay. So this is the reference model here. This is the optimization model that I showed previously. Here, this is how I have divided my design region. So here you can see I have my reference magnetic model. So here you can see that I don't have any CAD parameter. So now the first step is to define the set of the design region. So here I will create the set target for the NGnet. So here I will specify the two parts of the design region. Okay. After that, here I need to confirm that the material of each part is well defined. So here one part is iron and one part is the air. Now I can apply the NGnet condition. So here, take this here. So this is my NGnet condition. Here I will specify the set of the design region that I have created. Here I can define my covariant matrix. So for example, I can start with 2 just to see. And here you need to create the grid that JMAG will use to distribute the Gaussian cell into the design region. So you have many possibilities. So here you can import some text file or CSS file you have, or you can use this tool to create to generate the grid. So here, for example, I can specify tool just to show you. Okay. So here you can see that how is distributed. Here, if you remember, it's recommended that you need to define the grid so that the cell, the Gaussian cell, will cover all the design region. So here we can see that here we don't have some Gaussian cell. So this means that the cell is not correct. So I will clear. I will try to increase this one. Create a new grid. Example. So here now the Gaussian cell is uniformly distributed on the design region. So now to take into account the symmetry of the two parts. So this is the symmetry line of the two parts. Here I can check this box, but you see that here the reference axis that JMAG will use to apply the mirror. So it will select the first axis of the coordinate system. So here the first axis of the global is the x-axis, but I want the axis to be coincident with this line. So this means that I need to create my own coordinate system. So here I come here, right click, I will create my own coordinate. So here I will specify x-axis to be coincident with the symmetry line. Yeah. I can define the name. Example. Okay. Then here I have my own coordinate system that I will use into the NGnet condition. So here I will select here. So this means that it will uniformly distribute the Gaussian into the two parts using this line as symmetry. So now I have finished. I can confirm the number of Gaussian. So here the number of Gaussian correspond to the number of node. So here I have 53. Okay. Now I can open my option tool. Yeah. So here I need to define the object function. So here I will create the response variable which correspond to the torque average. You see, integral. I will link with the rotor condition here. I will define the name of this variable. Then okay, I'll do the same for the torque ripple. Here I will select the calculation method or ripple rate. I will link with the rotor condition and I will define the name. And then I will click OK. So now to create my object function, I will click here on add. So for example, you have many options to define. So you can define, for example, here right, I want to maximize the torque average. Here I use the torque and here I select maximize, right? Okay. Do the same with the torque ripple. I want to minimize the torque ripple. Here I select torque ripple, want to minimize. Okay. So here I can add several objective function. So in the next step, I need to select which solver I want to use. So here I have defined several objective function. This means that here I will use multi-objective function solver. Yeah. So if you remember the recommendation, so the number of population should be equal. If I go back, here this is the formula. So the number of population or children should be higher than the number of Gaussian plus 1, because here we have two material design. Yeah. So this means that here I put 54. 54. Here you can also define the shape continuity between the design part. So this means that during the calculation, sometimes you will have some cases where the part is divided into multiple parts. So you can add some limitation. So you can also say that you want the part to be not divided. So you can use this option, or you can define the maximum number of division for each part here. So I will keep the default one. Here you can define the setting to control the result, because when you are using this this method to run the topology optimization, you will have several cases, and this means that the result file will be very higher. So you can use this option to reduce the size of the result. So here you can see that you can keep the result. You can keep only the optimal case that are on the Pareto front, or you can say that you can just keep the best objective function of each cases for each generation, or you can save all the cases if the computer, if you have a good computer. Yeah. So here I will select. You can select, for example, save the best objective function of each generation. So here the standard value is 10 times the number of the design variable. So the number of design variable correspond to the number of the Gaussian. So, but for the demonstration, I will just put one just to show you how to run it. Here, during the calculation, it is not possible to directly confirm how the objective function is calculated. So you can define this output file, so that JMAG, during the calculation, JMAG will export all the value of the objective function of each case into the CSV file that you can check during the optimization. So here you can directly run the calculation, and you can also use a remote system to run the calculation on your workstation that you have that is connected to the network. So here I can click submit, save. So here it will open the scheduler. So here you will start, it will generate the first initial generation. Yeah. So you see, this is the first generation, which correspond to, if you count, you see that it correspond to the number of the Gaussian. So I will stop it. Stop. Stop all. So here I will just show you the result. Okay, so this is the reference model that I showed before. This is the observed model. Here, here we have the first model that I run. I use the genetic solver. So if I open here, I define the finesse function, and here I use the GA solver. Here I define this number of generation. Here I can show you the result. So here I just plot the finesse function over the torque average. You see that's how the finesse function is going. So you can see that here you have some maximum value. You can also plot the finesse function over the torque ripple just to see the distribution. So for example, here you can see that here I want to minimize the torque ripple and I want to maximize the finesse function. So this means that one best case can be selected here. So if I show you these cases, so this is one best cases that you have. So here you have several cases. Into another example, so I use the multi-objective solver. Maybe I can show you. So here I use the process that I done before. Here I select the multi-objective solver. I can also show you. I can show you some cases here. I can also show you the scatter plot between the two objective function. So you have something like that. Yeah. But if you want to well have the Pareto curve, so you need to run for several generation. Yeah. So I can also show you the comparison with so I make some comparison of the torque. So maybe I can show you. Okay, so for example here I can show you selected. Oh, okay, maybe I need to do it again. So here I will use these cases. Well, show. I will generate the torque graph. So this is the torque graph. Here now. So here I will find the result of the reference model, for example. Okay, so this is the reference model. I will select the torque, the graph. I will add it to this torque. Click show. Thing here. See. So here you can see the difference from the result of the objective of the optimal model with the reference model. Yeah. So you can also compare the average. So this is the average of the reference model, and here this is the average, the torque average of the optimized model of the optimal case. Okay, I also perform some advanced model. So here, sorry. So So yes, that I also add some constraint to control the shape, the shape of the iron part and the shape of the air, because generally into the motor, the surface or the volume of the iron is large than the volume of the air. Yeah. So you can also define this kind of content in order to improve the result. So I can show you some case. Yeah. Yeah. So here, this is the distribution. This is the scatter plot of the torque average versus the rotor iron. So here you can see that the best case are located into this iron, for example. So if you want, this is the reference. This is the reference IRA of the reference model, and here this is the reference torque that I calculate from the reference model. So is that here the optimized cases is lower than the IRA of the reference model, and the torque is higher than the torque of the reference model. Okay. So, okay, so I show you how to compare, how to make some comparison between the best cases. So here you can see that with the multi-objective objective solver, you'll be able to get some good cases than the JA solver. Yeah. So for the advantage, you have a lot of advantage of this method. So for example, you can use up to 256 material. Yeah. You can also use parallel processing. You can use the part that you have defined into the FM conductor, into the design region. So what is the important advantage is that the step is very simple, but it can be a complementary of the classical method. So this is the topology process. This is the classical one where we start with the CAD variable. So you can start with the topology optimization to find the new shape, so the new topology of your machine, and then you can define some CAD variable in order to find the good parameter that can allow you to represent the model that you have here. So we also have some limitation when you are using this method, is that you cannot use it for some analysis or some coupling analysis. For example, you cannot use it for thermal and electrical analysis, and also to perform some microthermal coupling or microthermal stress coupling. So you can only use that for magnetic structural analysis or coupling. Yeah, and you cannot define several design region. For example, you cannot define the design region for the rotor and the design region for the stator in same time. So this is not possible. You can also customize the solver. So you can only use two solver, so JA solver or multi objective solver. You can also use this option, so the add measurement, that allow you to create a variable to control the part volume either others. And you can also use some condition. So here, this is the condition that you cannot use. You cannot use it into the design region. So if you define some part here, so this means that you cannot use this part into the design region. So another information that I want to give you is that we have also implemented another method, which is the density method, which is very fast than the advanced method. You have seen that the advanced method require a lot of cases, and you need to have some good computer in order to generate in order to obtain the Pareto curve. So it take a long time, but with this method you will you will run in a few minutes. You will get several cases, and this you can run it into the single computer. Yeah, so this is the fast method, but it's limited. Here you cannot also define or customize the objective function than here. So because here you have some predefined function that you just need to select and run the calculation, and here you cannot use several objective function. You can only use a single function. And the next developer, so the next feature that the developer of JMAG will implement below. So the first feature is that they will try to include some periodicity in the topology, because if you look this half model, yeah, we have 2 pole and 9 slot. If you use the actual method, you need to use all the shape of the rotor, but if you want to take into account the periodicity, you cannot do that with the actual method. But with the next method, you can just specify this area as the design region, and based on the periodicity, it will automatically apply the same distribution into this path. This means that this is the good feature, because it will reduce the number of Gaussian, and it will also reduce the simulation time. Yeah. And the next feature is that you will also use the script to generate some response variable that you can use to define the objective function. Yeah. And also for the method that I present before, the density method, the fast method, they will also introduce the structural analysis, so it will support the structural analysis. So for the other demonstration or other function of JMAG, so you can find it into YouTube. So we have several video, or you can go to our webpage. You can discover our application catalog, which contain several examples of machine. So we have different office in Europe. Yeah, so where we are based in, the headquarters is in France, but in the world we have different office. So thank you for your attention, and if you have some question, please feel free to ask me.
Thank you, Didier. Thank you very much for your presentation and demo. So to the attendees, you can still ask your question on the chat box of the GoToWebinar panel. So we will go through some of them now, as we have some time. So the first question I would like to ask to you, Didier, is can the optimization include a mechanical stress analysis of the machine?
Yes, you can include mechanical stress. Maybe I can show you some example also that I prepare. So before I told you that with the NGnet method is available for magnetic and structural calculation. So here, this is one example of topology optimization that I run by coupling magnetic and structural. So here I define some stress, so I want to optimize. Sorry. So here I measure the volumetric stress into the rotor, and this is I can use that for the objective function, so I can minimize during the optimization. So if you remember into JMAG, you can also create some analysis group. So this is what I have done. Then here I have coupled my two analysis, magnetic and structural. Yeah. So I can show you my objective function. So here you have the objective function that I defined to minimize the stress. Yeah. So here I can show you some result. You have some result here. Okay, so you have some bad case, but that is working. So we can do that into JMAG. So, another question?
Okay, thank you, Didier, for this one. Another question is someone would like to know if the this optimization technique is available on JMAG version 18. But I think that this NGnet method arrived with the JMAG 19 version. Can you confirm, Didier?
I think you have it into the version 18.1. You have
18.1.
it.
Okay.
Yes.
Yeah. Okay, so this NGnet method is available on JMAG 18, JMAG Designer 18.1. Okay, so I think we have covered all of your questions. We still have some time, so if anyone has a question, please ask it now. In the meantime, I would like to inform you that the recording of the webinar will be available on our ProAssist website in a few days. You will be notified by email when the recording will be available, as we had several questions about this topic. Okay, so it seems that we don't have any other question for today. So I would like to thank everyone. Also, thank you, Didier, for your presentation. We always appreciate to have a lot of attendees as today. Don't forget to visit regularly the ProAssist website with the webinar and training page to be aware of the next webinars and trainings. Thank you again for joining us today, and we'll see you next time.